In this video, we are going to think about where the electrons go in any given orbital. So in a previous video, we talked about what orbitals are, the s, p, d, and f orbitals, and they're in different shells. So in this video, we are going to think about where are the electrons that we know are in an element like carbon. What orbitals are they in? So all of the previous information, the Schrodinger equation, the quantum numbers, is all developed on elements or really based just on hydrogen, which hydrogen has one electron. So there's no interference. What does that look like? So hydrogen has one electron. It lives in the lowest orbital, the lowest energy orbital, which is 1s. So typically we would draw that as 1s with one electron. You could also say 1s1, where this is the n value. So in this case, n equals 1. The s tells us that L equals 0. This value tells you that it's one of the two electrons, and so that is equal to plus 1/2 in this case. And the m sub L tells you which orbital it is, which will make more sense when we start to think about p orbitals, but that's also 0. So now we know the 4 quantum numbers that are specific to an element. So helium has 2 electrons, and they are both in the 1s orbital. So where do we put those? So these 2 electrons are in the 1s, and we know that the 1s can have 2 electrons. And so those 2 electrons are both in here. And we annotate electrons as these arrow with just one side. And so it looks like this. And we have 2 of them, and they are both in the 1s. We can draw it like this, and we can write it as 1s2. So the Pauli exclusion principle states that no 2 electrons in the 1s orbital or any other orbital can have the same 4 quantum numbers. This means that the 2 electrons must have opposite spins because m sub s tells us that they have plus 1/2 or minus 1/2. So if we were to think about the 1s with 2 electrons, the quantum numbers are going to be n equals 1, L equals 0, m sub L equals 0, and m sub s equals plus 1/2. And for the other one, it's n equals 1, L equals 0, m sub L equals 0, and m sub s equals negative 1/2. These m sub s values tell us about the Pauli exclusion principle. And the Pauli exclusion principle states, very simply, these 4 quantum numbers have to be different for 2 electrons in the same orbital. And we see that with plus 1/2 and minus 1/2. So all electrons and all orbitals can hold 2 electrons, or a suborbital. Those 2 must have opposite spins and opposite quantum numbers. So when we think about the orbitals, we need to ask ourselves the energy orbitals. In a hydrogen atom, all of the orbitals in any shell have the same energy. This means that they are what's called degenerate. Degenerate means same energy. In a multi-electron atom, the energy of each orbital within a shell changes. So if we think about this graphic, where we know that the energy goes this way, what do we see and how do they look at these different things? If we start to look at the orbitals for just any given shell that contains the s, p, d, and f orbitals, what we see is that the s orbital is lower in energy than the 3p orbitals. Well, that's not 3p, but just that there are 3, so we'll just call that the p orbitals. Then the d orbitals, so there are 5d, and then 1, 2, 3, 4, 5, 6, 7 f orbitals. So as the energy increases, or as in any shell, the s orbitals are the lowest energy, the p, d, and f are in the other. As we add electrons into these, they need to go from lowest energy to highest energy. So they will first go into the s, second into the p, then into the D, and then into the F for any given shell. So if we think about the n equals 5 shell, the 5s, the 5p, then the 5d, then the 5f. Now there are some quirks or irregularities when we start to look at the higher energy orbitals, and we'll talk about those in just a second. So we need to think about shielding. Shielding basically says that the nuclear charge, in this case we're going to think about lithium, which is 3 plus. So if we think about lithium, there are 3 electrons. We have the 1s, and then next comes the 2s and the 2p. So those 3 electrons are going to go 2 into the 1s, and the last one goes into the 2s. So these 2 electrons in the 1s, we have another electron out here in the 2s. So I'm going to annotate those as blue dots. So the effective nuclear charge, or Z effective, tells you how much of the nuclear charge this electron is going to sense. So fully filled inner shells shield the outer electrons. This basically means that this electron out here, indicated with the arrow, probably feels less of the nuclear charge because the 2 inner electrons are going to neutralize some of that charge. It's not quite 1-to-1. In a later video, we will talk about how you can calculate the Z effective and other information. But this is going to alter how things behave as we move forward. So the orbitals get closer together in energy as we get further from the nucleus. So we know this to be true if we were to think about ordering just n equals 1 through n equals 5. So n equals 1, n equals 2, n equals 3. They should get closer together. Oops, I feel like n equals 5 is not quite right. So we'll just move it down here. They basically get closer together as you get further from the nucleus. So this is going to be observed when we think about these other orbitals. As we go from n equals 1 to n equals 5, we have access to other orbitals. So we have the 1s, then we have the 2s, then we have the 2p, 3s, 3p, then we see the 3d, 4s, 4p, 4d, and then we can see the 5s is here. So if we look at these, we can see some irregularities. Irregularities basically means that when we get out here, if we draw a line from the 4s, it's slightly below the 3d. So we're going to start to have to think about the patterns of different things and how this structurally changes how electrons look. So there are some tips and tricks on how to remember this, and we'll see those as this video goes forward. But electrons are filled according to the off-bound principle, which says that we go from the lowest energy to the highest energy. So if we know the order of the orbitals, we can put them into the right place. And it's also important to note that electrons are filled using Hund's rule. And Hund's rule states that the lowest energy state is to have parallel electrons in degenerate orbitals first. So in the p orbitals, that means to go 1, 2, 3, 4, 5, 6. And the same thing is true in the d orbitals. So we can see this in both types. So in summary, because after this, we are going to start putting the electrons in orbitals. Lower energy levels fill prior to higher energy levels in this order. On your slides, it's going to be a little bit different. So the 1s, then the 2s, 2p, 3, so on and so forth. Each orbital can hold 2 electrons of opposite spins. And degenerate orbitals fill with a single electron first, then a second electron is added to each orbital. So let's look at a graphic that might help us figure out how to fill these orbitals. So if you write the following, where each orbital, so each n has an additional orbital, five p So if we have this graphic, and so it turns out not all of these orbitals exist, so the 6f does not. But if you fill in a diagonal pattern, then, so this is 1, 2, 3, 4, 5, 6, 7. This allows you to remember that so it would be the 1s, let's make so we'd fill the 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on and so forth. So you'll go in this diagonal pattern that's going to allow you to basically follow along. There are some tips and tricks based on where elements are located in the periodic table that will help with this, but at some level we need to think about just memorizing this information. So let's look at some examples. So we will do a selection of these. You should think about all of them. So I'm going to so we're going to fill it in a table, number of electrons, then we're going to draw, then we are going to write. I will use these two terms, both draw and write, and we need to make sure that you are answering the question that is postulated, whether it is drawing or writing, because those are asking for different information. So lithium has 3 electrons, beryllium has 4, 5, 6, 7, 8, 9, and 10. So based on that previous information, we're going to start with the 1s, 2s, 2p. And so I won't quite have enough space to fill all of these out, but that's okay. So we're going to skip some of these, but as we do this, we want to make sure that we fill each orbital completely before we go to the next. So for lithium, it is 1, 2, 3, which it is 1s2, 2s1. Basically, this means that the elements in the first one, we fill up the 1s, then we add 1 to the p. Beryllium, 1, 2, 3, 4, 1s2, 2s2. So carbon has 6. So we add 2 to the 1s, 2 to the 2s, and then the 2 electrons in the 2p are filled using Hund's rule, where we see this. But we write that 1s2, 2s2, 2p2. So when we write it, it doesn't annotate that they are filled following Hund's rule, but it does imply that because the writing and the drawing are important. We have 7 electrons for nitrogen. You see this? We're 1s2, 2s2, 2p3. So in fluorine, we have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 1s2, 2s2, 2p5. And neon has 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, it's important to note that the order of the degenerate orbital filling is somewhat irrelevant because it doesn't matter which one because they're all the same energy. But now we can determine the number of electrons, from the periodic table. We can draw these. You have to label your orbitals, 1s, 2s, 2p, etc. And then we can write them in this pattern. So what about potassium? So potassium is element 19, and it has 19 electrons. So we can fill these out. So we have the 1s, 2s, 2p, 3s, 3p, 4s. So don't forget, the 4s fills before the 3d. So then we just put in our 19 electrons, making sure to follow the rules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we can also write this as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, this is just element 19. What about if we were thinking about element 100 or 80 or something like a different type of element with a lot of electrons? We could be writing and drawing for a very long time. So the reality is there's a shorthand, and that shorthand is using the noble gas configuration. So the noble gas configuration says this, that this configuration right here is the same as a previous noble gas, argon. So argon is element 18, and it has 1s2, 2s2, 2p6, 3s2, 3p6. So this is the noble gas configuration, or the noble gas electrons. So what is really different is we have argon as the inner shell, and then we have the 4s1, and so this is potassium. You could also draw this as argon 4s, 1 electron for potassium. And so you can do this for any of them. It needs to be the noble gas of the previous shell. So you would identify your element, go up one row all the way to the right, and you can use that noble gas configuration. For a noble gas, if I ask for the configuration of argon, the noble gas of interest would be neon. So we can do this for any set of electrons in any element. So let's write and draw the electron configuration for the following elements. A couple of things. It says for strontium, we can use the noble gas. None of the others do. So for graded assignments, you will either use this one or the other one. So bromine has 35 electrons. And so it is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So now we're going to put in our 35 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4, 5. So we can see that this is the drawn electron configuration for bromine, and you would write that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. So we can see this for all elements, and we can do this. So let's look at phosphorus, which has 15 electrons. We have the 1s. Oops. Got a little excited there. The 2s, the 2p, 3s, 3p. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we can see that this would be 1s2, 2s2, 2p6, 3s2, 3p3. So strontium. Strontium is element 38. So it turns out that the noble gas configuration is krypton, then the 4s, and there are 2 electrons, or krypton 4s2. So we can set this up in either ways. You should try the configuration for arsenic on your own. So we can do this for any number of electrons or any compounds. We can also start to think a little bit more specifically about the 4 quantum numbers in an electron. So we previously talked about what they mean, but now we need to know. So we know that the 4p has 3 different orbitals. When we draw the 4p as 1, 2, 3, 4px tells us that it would be one specific element or one specific orbital. So for the 4px, we know that n equals 4, L equals 1, M sub L equals pick any value, 1, and M sub S equals plus 1/2. So in this course, we can select any value for M sub L that is allowed, any value. The 3 allowed values are -1, 0, and 1. You can pick any one. Same for M sub S. But the electron can only be in one orbital. So in the 5dxy, we have n equals 5, L equals 2, M sub L, any allowed value, I'm going to pick 2, M sub S equals -1/2. Again, any value. So for 7s, n equals 7, L equals 0, M sub L has to equal 0, it's the only allowed value, and M sub S equals plus 1/2. So we can pick any of these values for any of the things. The location of electron in either the inner or outer orbital determines how reactive this element can be. This tells us that electrons can be different types. So we can classify these as core electrons or valence electrons. So let's look at silicon. So silicon has 14 electrons. Whoops, that's not how we draw that. So silicon is Si, and so we have the 1s, the 2s, 2p, 3s, 3p. So we're going to put in our electrons. We look like this. If we were to write the noble gas configuration, we have neon, 3s2, 3p2. These electrons here are what we're going to call the core, which is why we can use the noble gas configuration. That is the inside, non-reactive portion. These electrons here are the valence electrons. So the valence electrons are the more reactive compounds. So we can look at both of these and say how many core electrons. So there are 2, 4, 6, 8, 10 core and 4 valence. As we move forward in this video series in the sections called 10 and 11, the valence electrons are going to be how we can predict how an element will create bonds or interact with others. So the core and the valence electrons can be predicted based on the periodic table. So it turns out that the periodic table, in addition to being organized by mass and changing atomic number, it also tells us about the orbitals. Because if we look at our periodic table, it's like this. It's not quite drawn to scale. But it turns out that elements here are the s orbitals. The p orbitals can be found here. Oops. And the d orbitals and down here are f orbitals, and we will highlight those, the last color, red. So when we look at the elements, based on their location, we can tell where the outer electrons are, whether it's the s, p, d, or f orbital. If you look at the periodic table all the way on the left side, there are 7 rows. So we have n equals 1, 2, 3, these are not to scale, 5, 6, 7. These are very, very wrong. But this row right here is going to be the 3D. And you could see that the 4s followed by the 3d followed by the 4p. We can predict the electron configuration based on any element. So bromine is right here. So we can predict that it is in the 4p block. And we can predict that based on where it is. So the noble gas of the row before is going to be argon. So we could say argon, 4s2, 3d10, 4p5. You can also memorize the order of the electron orbitals and just count your 35 electrons. All of this is helpful. You can do it either way. This just gives us insight into that. So let's look at the end of this video about what happens when there are rule-breaking elements. So transition metals. Transition metals have their outermost electron in the d orbitals. If you remember back to this graphic, the 4s is slightly lower in energy than the 3d. So we're going to fill the 4s first, then the 3d. So chromium. Chromium has 24 electrons. So the noble gas is argon, 4s, 3d. And there are 6 electrons. So traditionally what we would have said is 1, 2, 3, 4, 5, 6, where we have a fully filled s orbital and a wildly incomplete 3d orbital. It is lower in energy due to how close the orbitals are. To promote, aka move, this electron here to where we would really get 4s, 3d with 6 parallel electrons. This works because of how close these electrons are. And it is lower in energy to have 6 parallel electrons than the fully filled s orbital followed by the d orbitals. So let's look at copper. This has 29. Oops, that's not 9. 29 electrons. So we have argon, 4s, 3d, and we see this in the parent complex. So it turns out that it is going to be lower in energy to fully fill the d orbitals to give us 4s with 1 and a fully filled d orbital. It turns out when you fully fill the d orbital, it drops in energy and is then inside the 4s. So this is lower in energy. So these elements here are the rule breakers you need to know. If you were to look at the d electrons, or the d orbitals, if we have chromium, and then we have copper, the rule breakers are 2 elements that are adjacent to one another, chromium and molybdenum. Then we have copper and silver. They follow the same trend. And then it turns out that there are several elements in the 4D where electrons are promoted into the s first, or into the d orbitals first, to where you will have 4s1, or in some cases 4s0. You need to know all of these. So let's write and draw the electron configuration using the noble gas for two metals. So palladium has 46 electrons. Its noble gas configuration is krypton, which means that the next is the 5s, followed by the 4d. And in there we have 10 electrons. So we would think it would be this. 2, 4, 6, 7, 8, 9, 10. But palladium rule breaks by taking both of the s orbitals and promoting those into the d. So what we actually get is 5s, 1, 2, 3, 4, 5. A fully filled d orbital. So where, oops, we forgot our krypton. If you were to write those, it would be krypton 4d10. You can include the 5s0. You can also omit it. Either one is fine. So for 10 has 50 electrons. So it would be krypton, 5s, 4d, 5p. And based on its location, we know that the last electron is in the 5p, and there are two of those. So we can also write that as krypton 4d10, 5s2, 5p2. These two can either be in this order, or it could also be written as krypton 5s2, 4d10, 5p2. Both are similarly correct. We can look at the electron configuration for any given set of electrons in any given orbital based on their location in the periodic table.